Previously, given a subspace U of a quadratic space, we defined its orthogonal complement to be all the vectors in V that are orthogonal to U. By orthogonal, I really mean that the bilinear form applied to V, U is going to be 0 at all U in U. Then we ask, is it true that V is always going to be a direct sum decomposition of U and U perp? And we show that this is not necessarily true in general. A necessary condition is that U must be regular, and that was how we introduced regular spaces. So let's review why U must be regular. Well, for this to be a direct sum, we need this intersection to be 0, but this intersection might not be 0. When would it not be 0? Well, if the radical of U, if U is not regular, then the radical of U will contain some non-zero vector V. And by definition, then V is going to be orthogonal to every vector in U. So V must lie in U perp, but V lie also in U, so this intersection is not trivial. Thus, a necessary condition for V to be written as a direct sum of U and U perp is that U is regular. This turns out to be a sufficient condition. Now we will show that U and U perp span the whole of V, and for that we will use the previous statement that we proved. As U is regular, we will use the statement that every linear functional on U comes from dot product with some element of U. Again, I'm saying dot product instead of the bilinear form because it's just shorter to say. Alright, so we want to show that V is spanned by U and U perp. That means that if I take a vector, little v, in V, I should be able to write it as a component U in U, right? And then V minus U should lie in U perp. In other words, given a vector V, I should be able to get an orthogonal projection U of V onto U. I should be able to define a projection of V onto U. Well, let's recharacterize what it means for U to be an orthogonal projection of V onto this big space U. Well, observe that for any U prime in U, taking the dot product of V with U prime is just equivalent to taking the dot product of U with U prime, because this component dot with U prime is just going to be 0. In the case when U is a one-dimensional vector space with a unit vector U prime, for example, then when we take this dot product, what we are saying is this gives us the component of V in the direction of U prime, and that's exactly determined by this U. So another way of saying is that this map V dot product with V is the same as dot product with U when we restrict them to U. When we need to dot product V with anything on U, we might as well just dot product this little u, because the other part of it doesn't matter. So in other words, we can decompose V as follows: if and only if there exists a little u in U such that this map is gonna be equal to this map. But this map is just a linear functional on U, and we said that every linear functional on U must be of this form. Right? So there must exist indeed some U such that this is equal to this. This U then would be an orthogonal projection of V onto big U, and so we can write V as U plus something in U perp. This shows that big V is spanned by U and U perp as desired. Now we will prove the uniqueness of the orthogonal complement. So suppose we have the following decomposition. What does it mean? This means that V is a direct sum of U and W, and that every vector of W is orthogonal to every vector of U. Then, in particular, this means that W must lie inside U perp, must lie inside this orthogonal complement. But on the other hand, because V is the direct sum of U and W, we know that the dimension of W must be equal to the dimension of U perp. So since W lie inside U perp and they have the same dimension, W must be equal to U perp. Thus, we see that if U is regular, then we can write V as a direct sum decomposition of U and U perp, and this orthogonal complement is unique. This decomposition is unique.